This is geometry lesson number 9. We're going to be studying inscribed and circumscribed polygons. An inscribed polygon is a polygon placed inside a circle so that all the vertices of the polygon lie on the circumference of the circle. You can see each one of these, starting at the left with the triangle, the rectangle in the center, and the pentagon over on the right hand side, all touch the circle with their vertices. All the sides form chords of these inscribed polygons. A chord is defined as a line that goes straight from one point on a circle to another. Next is a circumscribed polygon. A circumscribed polygon is around a circle if its vertices are outside the circle and its sides are tangent to the circle. By the way, you must understand that tangent means to touch. Okay? Look at these three figures here. All the way on the left-hand side, we have a pentagon that is circumscribed around the polygon. Do you see that it touches the sides of the circle and the vertices are on the outside? Now, there's also a little pentagon inside that, in the gold color, that's inscribed in. This is a good way of keeping in mind what it means to be inscribed. Inscribed always means it's going to be in the circle, and circumscribed means it's around the outside. The next subject in this lesson is triangle centers. A center of a triangle is where constructed lines cross, and this depends on the construction of those lines. There are actually many types of centers. We're only going to deal with 4 in this lesson. The first is called a centroid. A centroid requires a line called a median. The median will always go from one corner or vertex to the midpoint of an opposite side, as shown in the drawing. Right through the vertex, right through the center of the opposite side. That is a median line. When we have 3 of those together from each one of the vertices, we have a centroid. And the centroid is very interesting because it is always the precise center of mass of any triangle. Next is the circumcenter. It is made by a perpendicular bisector at right angles to the midpoint of each side. You notice this is different from an altitude because it doesn't go from a side to a vertex. It goes from the center at right angles to wherever it ends up on the other side. Where all 3 intersect is the circumcenter. And if you look carefully at the drawing, you'll see that's also the center of a circle that of an inscribed triangle. Third is the incenter. This is made by an angle bisector or bisectors, and goes on out through the triangle wherever it happens to go, and where 3 of these come together forms what's called an incenter. You notice in this case, by the way, that incenter is the center of a circle which is inscribed in a triangle. Finally is the orthocenter. The most important thing to remember about this is that the word ortho comes from Greek, and it means upright, which of course is going to make it an altitude of a line. It's going to be, we're always going to have one line that's upright to a side. Now, how is this different from the in-center, it's simple. This doesn't necessarily go through the center of a line, but it does go through the vertex. It's just the way that we set up an altitude when we want to try and determine what the area of a triangle is. So when we have all three of these, we have the orthocenter. Remember, ortho is Greek for upright. The next subject is locus of points. Locus of points is a relatively simple concept. It can cause some confusion, but stick with the idea that a locus of points is simply a set of points that satisfies given conditions. So, of course, to have a locus of points, you must have some given conditions. An example: the locus of points at a given distance from a given point is a circle. Matter of fact, it's actually the definition of a circle is a point and a radius. So if we have a point, the locus of points that's a given distance from it will always be a circle around that, and that satisfies the locus of points. The next example is locus of points equidistant from 2 points, and this is going to be a bisector of a line between them. We have points P and Q, and we're trying to find a locus of points equidistant from them. Of course, all of the points on the red line perpendicular and bisecting line PQ will satisfy that. The next example is a locus of points equidistant from 2 rays of an angle, and that's going to be a bisector of that angle. We couldn't have a line outside because it would be at various distances from the 2 rays. And the final one we've got here is an example of a locus of points about a certain distance from a line segment. Okay, there's a line segment, and there in red around line PQ are all of the possible points that could be a given distance from it. You'll notice it forms a racetrack. This is always going to happen with a line. Of course, you're going to set up 2 parallel lines above and below line PQ. They'll be equidistant. And the reason that it forms the racetrack is from point Q, holding that distance of the parallel will cause an arc to form, literally a half circle. And the same at point P. Locus of points is very important in analytic geometry. It's also important in algebra, and you'll see it often in calculus.